Today we're going to talk about proving lines parallel. Up until this point, we've been looking at situations in which we know lines are parallel. In fact, that's been the hypothesis of the rules we've been looking at. We've known lines were parallel, and we were allowed to draw conclusions about the angles formed by transversals. For instance, if I have these two lines, and I tell you they're parallel, well, you can now draw conclusions about corresponding angles, about alternate interior angles, about same-side interior angles. And those are all based on the rules that we looked at previously. But now we want to ask the question, what happens if I don't know that two lines are parallel? For instance, this example. If I don't know these lines are parallel, what conclusions can I draw about the angles? The short answer to that question is none. There are no conclusions I can draw about any of these angles with respect to the rules we've learned in this chapter. So what we want to be able to do then is sort of work backwards and see if we can look at the angles and determine anything about the lines themselves. Can we prove lines parallel? That's what we're going to try to accomplish today. Before we get into that, I just want to review this idea of conditional statements and the converse of conditional statements. You may remember that to form a converse, you take the hypothesis and the conclusion of a conditional and you switch them. And that's how you form the converse. Pretty straightforward. Let me just give you one example. It's a conditional statement. It's an if-then statement. It says, if the light is red, then I may not move forward. We could ask the question, is that a true statement? Certainly we could try to equivocate and tear it apart and make nonsense out of it, but I think we'd all agree for the most part, if you're driving a car here in the United States, if the light is red, you're not permitted to move forward. The converse is formed by taking the conclusion, I may not move forward, and putting it in place of the hypothesis, the light is red. Taking the hypothesis and put it in place of the conclusion. Let's do that. Pretty simple task. This is a conditional, this is the converse. Notice the truth values. I think most of us would agree that this is a true statement. However, when we look at this one, if I may not move forward, then the light is red. I think most of us could come up with a counterexample. For instance, if you're at an intersection and there's a police officer directing traffic, you may get a green light, but if he has his hand up, you're not permitted to move forward. And so in that instance, you'd find that this conditional, that is the converse of the original, this converse would be false. So we see that sometimes conditionals and converses have different truth values, and that's important to keep in mind. Let's look at another example. The conditional says, if you are watching Mr. Picard's video, then you have access to YouTube. We could ask the question, is that a true conditional? And the answer is yes. I know that because I post these videos to YouTube, and unless somehow you stole my computer and you're watching them there, I suspect you must have had some access, some way to access these videos on YouTube if you're watching them. Let's look at the converse though. The converse says, if you have access to YouTube, then you are watching Mr. Picard's video. Somehow I suspect that's not true. If it were true, by the way, I'd be a millionaire. But it's not true. So we have a conditional that's true, we have a converse that's false once again. Let's look at a third example. This example says, if the non-common sides of two adjacent angles form a line, then they are a linear pair. It's a geometric example, of course, from something we've already studied. We could ask the question, is it true? Yes, it is true. Let's look at the converse. Here's the converse. If two angles are a linear pair, then their non-common sides form a line. You'll notice I changed out the pronouns a little bit here. We have they, and of course that was in the conclusion. When I moved it to the hypothesis, I changed they for the two angles themselves. Don't worry about that. That's okay. That's permissible. But if we ask the question, is the converse true? The answer to that question is yes. Converse and the conditional are both true. And so we know that we can form a nice biconditional from this. It would read, the non-common sides of two adjacent angles form a line if and only if they are a linear pair. So that's a review of converse, and it's important that we understand that because The rules we look at today are actually just the converses of three rules that we articulated earlier. The first rule we need to look at is called the converse of the corresponding angles postulate. If the original rules we looked at yesterday were a mouthful, these are even more so. The converse of the corresponding angles postulate. I will simply start by stating the corresponding angles postulate. The corresponding angles postulate says, if a transversal intersects two parallel lines, then corresponding angles are congruent. So the converse of that must be, if corresponding angles are congruent, then a transversal intersects two parallel lines. Let me write that down. If corresponding angles are congruent, then a transversal intersects two parallel lines. Okay, what does that mean though? Let's just take a look. Suppose I have a transversal in two lines here. These are two coplanar lines in the transversal. Notice I don't know that these are parallel lines. I have no idea no way of figuring that out. I certainly don't have symbols on them, nor do I have any sort of information that tells me that, and I certainly haven't told you that. But if I give you the following information, suppose I tell you that this angle measures 80 degrees, and this angle measures 80 degrees. The fact that these two corresponding angles are congruent allows me to conclude that these two lines are parallel. So I can work backwards. Yesterday we talked about the fact that if two lines are parallel, a transversal intersecting them will form congruent corresponding angles. Today we're talking about the fact that if I know these corresponding angles are congruent, then the lines must be parallel. It's the converse of the corresponding angles postulate. Let's look at one more example. Suppose the measure of this acute angle here is 73 degrees, and this acute angle here is 73 degrees. We'll ask the question, are the lines parallel? Yes, they must be. By the converse of the corresponding angles postulate. If corresponding angles are congruent, then a transversal intersects two parallel lines. That's the rule. The next rule we need to look at is called the converse of the alternate interior angles theorem. Woo. Yeah, let's write that down. The nice thing about these rules is that I don't really even need to tell you what they are. If you know the alternate interior angles theorem, then you should be able to ascertain what the converse of the alternate interior angles theorem is. The alternate interior angles theorem says that if a transversal intersects two parallel lines, then alternate interior angles are congruent. So if we switch that around, we end up with, if alternate interior angles are congruent, then a transversal intersects two parallel lines. Let's write that down. If alternate interior angles are congruent, then a transversal intersects two parallel lines. It's the converse of the alternate interior angles theorem. How does that work in practice? Let's look at another example. Here we have a situation in which a transversal is intersecting two lines. I don't know whether the lines are parallel, but I'd like to know. Suppose we're given the following information. We know that these two angles are 86 degrees. You'll note that these are alternate interior angles, and they're congruent. And this converse of the alternate interior angles theorem says that if alternate interior angles are congruent, then a transversal intersects two parallel lines. So while I come to this ignorant of whether or not these two lines are parallel, I can conclude, based on my analysis here, that they are in fact parallel. That's the converse of the alternate interior angles theorem. One last rule we need to look at. It's called the converse of the same side interior angles theorem. Again, you might be able to guess what it says. The same side interior angles theorem says that if a transversal intersects two parallel lines, then same side interior angles are supplementary. So the converse of that must be, if same side interior angles are supplementary, then a transversal intersects two parallel lines. Let's write that down. And there we have it. And the application of this rule works very similar to the ones we've just looked at. if I have a situation in which same side interior angles are supplementary, such as this situation here. I've got an angle that measures 130 degrees and another angle here that measures 50 degrees. And I can see that they're same side interior angles. Their sum is 180 degrees, which means they're supplementary. Therefore, I can conclude that these lines are parallel. And that's how we use these three rules. They allow us to look at the angles and make a determination about the lines. Yesterday, when we talked about the conditionals themselves, they allowed us to look at the lines and make a conclusion about the angles. So we're sort of working in reverse at this point. There is one more rule we need to discuss. I'll call it the parallel lines theorem. The parallel lines theorem says that if a line is parallel to two other distinct lines, then those two other distinct lines are parallel to each other. In some ways, the parallel lines theorem can be thought of as the transitive property applied to lines. Basically says, if I have line L parallel to line M, and line N parallel to M, line L parallel to M, and line M parallel to line N, then I can conclude that line L is parallel to line N. Pretty straightforward. By the way, it also works with more than two lines. In other words, as soon as I begin to determine that line L is parallel to line M and line M parallel to line N, I may find out later on that line N is parallel to line O, and perhaps that's indicated with three parallel signs here. Okay. I can conclude that line L is also parallel to line O. You notice in some sense it's very similar to the law of syllogism. I'm allowed to connect through these different pieces of information, and then I can sort of jump from one to the next, from L to O. So that's the parallel lines theorem. Okay, I've put a diagram on the board. You see there's a number of line segments, a whole lot of points identified, points A through H. And what I'm going to do is I will list some facts about angles that I happen to know. And in the context of what I tell you, we want to be able to determine if any of these lines are parallel, and we want to know that for certain. So the first question I'll ask, question number 1. If angle CIJ is congruent to angle IDE, then what lines must be parallel? Notice this is a question, not necessarily a conditional statement, although it does have the if and the then in it. If this is true, which lines must be parallel? So the first thing we need to do is find these angles. Angle CIJ. CIJ, that's this angle right here. And I'm saying that it's congruent to angle IDE. So we need to find an angle IDE. Angle IDE is this angle here. Okay. The next thing we need to do is ask the question, are those angles of any sort of known relationship with respect to a transversal? And I think if you look here, this line AC and line FD, you can see that this line segment ID is part of a transversal there. And with respect to that transversal, these angles are alternate interior angles. Okay? It looks something like this. And we have this and this known to be congruent. What can we conclude? We can conclude that line AC is parallel to line FD. I do want to point out one thing. I know it doesn't look parallel in the diagram. And so you could argue with me and say, well, then those aren't congruent, and that's fine. But we have to be able to sort of think inside the box. If I'm telling you that these angles are in fact congruent, then these lines must be parallel, even if it doesn't look like it. Let's try another one. Okay, similar question. If angle BJC is congruent to angle AEJ, which lines must be parallel? Again, the way that we figure this out is we first identify these angles. BJC. BJC, that's this angle. And angle AEJ. AEJ. That's that angle. It says which lines must be parallel. Again, we need to try and determine, are these angles related in any way? And I think if you look at this line AE and line BD, And then direct your attention to this line CE. CE is actually a transversal intersecting lines AE and BD. Here's a transversal right here. And so relative to that transversal, these are corresponding angles. Converse to the corresponding angles postulate says that if corresponding angles are congruent, then lines are parallel. And so we conclude that line BD is parallel to line AE. Let's look at one last example. Okay, here the fact given is that the measure of angle BGE plus the measure of angle GEC equals 180 degrees. There's another way I could have stated that. I could have simply said that angle BGE and angle GEC are supplementary. However we state it, we still know the same information. Let's identify the measure, let's find angle BGE. BGE, we'll just put a number 1 in there. And GEC, GEC, we'll call that number 2. Question, do we know now whether any of these lines are parallel? Again, we have to begin to look around and see if we can identify these two angles as an angle pair of some sort. And when you look at it, you find that they're actually same-side interior angles. If you look at this line BF as one of the lines, and CE as the other line, you find that this is my transversal, and those are same-side interior angles. The most recent rule that we learned, the converse of the same-side interior angles theorem, says that if same-side interior angles are supplementary, well then these lines must be parallel. So I find that BF, line BF, must be parallel to line CE. I'd encourage you to work through the review problems in the text. I do want to at least alert you to one thing. A good number of the review problems as you get further along in the text are actually probably better questions for section 3.2, the last section we talked about. So be aware of that as you work through them. If you have any questions, send me an email.